So that points to something really crazy happening in the early universe in terms of early star formation, early galaxy formation.
And so if that's the case, is that a major rewrite?
Yes.
You think so?
Yes. But we'll see. I could well be wrong.
There is a grave problem with our universe. The James Webb Space Telescope has made a groundbreaking finding that challenges our understanding of the origins of galaxies. It has discovered a crucial component of life at the beginning of the cosmos. The finding, which is the first known detection of an element other than hydrogen in the cosmos, is a cloud of carbon in a far-off, compact galaxy as it appeared only 350 million years after the Big Bang. A preprint of the results is available on AR-14, and they have been approved for publication in the journal Astronomy and Astrophysics. Scientists classify elements heavier than hydrogen and helium as metals. Co-author Roberto Molino, a professor of experimental astrophysics at the Cavendish Laboratory for Cosmology at the University of Cambridge, said in a statement, "Earlier research suggested that carbon started to form in large quantities relatively late, about 1 billion years after the Big Bang. But we found that carbon formed much earlier. It might even be the oldest metal of all. This is due to the fact that these elements, aside from lithium and hydrogen, were created in the blazing furnaces of stars and dispersed throughout the cosmos by stellar explosions known as supernovas. It was previously believed that it would take several star lives for the manufacturing and seeding of heavy elements to become broadly accessible and heavy enough to produce planets. However, James Webb's most recent discovery has called into question this assumption. In the far-off galaxy known as GSZ-12, which has a mass 100,000 times smaller than the Milky Way, James Webb discovered signs of oxygen and neon mingled with a robust carbon signal. It is unknown exactly how carbon might have created at such an early stage in the history of the cosmos, although it is possible that stars imploded with less energy than previously believed. The scientists hypothesized that rather of being pulled into the black holes created by collapsing stars, carbon may have been able to escape and seed the early cosmos earlier than anticipated, since it would have formed in the outer shells of the stars. This suggests that life may have begun much earlier in the cosmos and may even have been too exotic for life in some circumstances, refuting the notion that life must have developed much later in the universe. In the universe, there are organisms quite distinct from our own that are more adapted to endure, prosper, and establish an interplanetary society. Maybe they're constructed of something completely different, like a crystalline or metallic set of structures, rather than well-known components like proteins. It just turns into a game of hide and seek at that point. Is anyone in the vicinity? This age-old query, which is currently recognized as the Fermi paradox, has plagued mankind for eons, especially as humanity expands its cosmic net and finds evidence of hundreds of worlds. We know a great deal more now than any prior generation, which is wonderful news. Planets orbiting other stars, or exoplanets, are abundant in our galaxy. A sizable portion of them are tiny, rocky worlds that resemble our planet in both size and substance. We've searched practically everywhere, and the components for terrestrial life, water, materials related to life, and accessible sources of energy seem to be there. The bad news is that we have not yet discovered intelligent life on any other planet. It is presently not possible to detect any indicators of potential microbial life in the atmospheres of exoplanets. Our enormous arrays of telescopes, both in space and on Earth, have not yet shown any persuasive evidence of advanced technology, artificial communications like radio waves, or the unmistakable indicators of large extraterrestrial engineering projects. It is significantly more probable to find non-intelligent life. For the most of its 4.25 billion year existence, Earth was devoid of any technological life at all, and human civilization is a relatively recent invention. Exists life somewhere besides Earth? The quiet thus far is deafening. Although the likelihood of discovering life elsewhere is yet uncertain, the possibilities do appear to be increasing. The Drake equation is a well-known list of the information required, albeit very speculative, to estimate the likely abundance of planets supporting life that was proposed in 1961 by astronomer Frank Drake. One of astronomy's most well-known attempts to address the subject of sentient life that possesses the capacity to interact with extraterrestrial creatures rather than just life itself is the equation. We're interested in talking aliens, not in microbes or intelligent clouds floating in midair. To be clear, this implies that there may be extraterrestrial life that the Drake equation would ignore, but it's a terrific approach to structure our queries around the likelihood of receiving alien signals. It begins with an aerial perspective of the demands of existence and then focuses on each part of the equation, progressively reducing or increasing the range of options and becoming more challenging to ascertain. The first question posed by the equation concerns the galaxy's average rate of star production. The Drake equation may not seem to have any relevance to real life, but that is part of its allure. It understands that in order to support a species, a planet needs stars, and vice versa. So let's begin by creating stars. This was the only figure we have concrete proof for a very long time. By examining the ratio of young to old stars, we can calculate the star formation rates in a large number of galaxies. In addition, we must comprehend the concept of the initial mass function, which describes the number of massive, minor, and intermediate stars that form inside a stellar nursery. The most current scientific findings indicate that this number ultimately amounts to around 1.5 to 2 stars created year. Although on the surface, this may not seem like much, consider the billions of years the cosmos has been spinning, the sum soon mounts up. The proportion of stars with planets is represented by the second number. This was a long-standing enigma. Although astronomers may conjecture, there was little concrete proof available until recently. We now have a large number of planets and star systems to evaluate from, thanks to Kepler, WASP, and other exoplanet studies. We estimate that there is approximately 1 planet for each star in the galaxy, which is our best estimate for this quantity. Of all, some stars, like our Sun, have numerous planets, while others have none at all, but in this case, averages are what matter. How many planets in a star that are able to host life is the next question. Here's when the obstacles start to appear. There is just 1 planet that is known to support life. Whether life ever existed on Mars is a topic of debate. What about planets like Europa that have subterranean oceans? We can identify habitable zones as regions on planets where liquid water can exist on their surfaces. What about planets near dwarf stars that are tidally locked? There is a lot of variation in the number. Currently, we estimate it to be between 3 and 5, but depending on how you define habitability, that number may be a lot lower or much higher. Then we truly begin to go into the unknown. What percentage of planets capable of supporting life go on to produce living things? Again, as of right moment, we only know of 1. Is this a 100%, or do we argue that our solar system only makes up 20% after taking into account Titan, Europa, Mars, and Venus? What percentage of planets with life beyond this support intelligent life? I wish you well in this endeavor. Out all the millions of species that have lived throughout Earth's history, only 1 has attained consciousness. Conversely, all worlds where life is known to exist possess intelligent life. Thus, the chances might not be that high. Perhaps. Giraffes are found on a number of worlds, but humans are not. This next section helps to distinguish the Drake equation from other thought exercises concerning extraterrestrial life. It poses the question of how many sentient civilizations manage to develop technology that allows them to broadcast proof of their existence, whether on intention or not, into space. For decades, humans have been emitting radio waves, and our output is only growing louder. Of course, intelligent civilizations can remain silent, but because we are only interested in those with whom we can speak, those with whom we cannot talk must provide some indication. The last component takes the longevity of these civilizations into account. It will be more difficult to locate one that broadcasts for hundreds, thousands, or even millions of years than one that lasts for barely 10 years before being destroyed by an asteroid or annihilates itself through nuclear war. Many said during the Cold War that since it resembled our society, the majority of foreign civilizations might not survive the nuclear era. For us, there wasn't much of a window between the development of radio technology and nuclear weapons. However, it might be argued that the difficulty of eradicating a civilization as a whole increases when a life form leaves Earth and begins to inhabit other worlds. Perhaps such civilizations rapidly became eternal, as one meteorite or epidemic wouldn't do it. When you add together all of these figures, you may get cautious approximations that result in a total value that is less than 1, meaning that humans are the only beings in the universe. Tens of millions of possibilities can be obtained with more optimistic figures. Drake's first projections ranged from 20 at the lowest to 100 million at the highest. Therefore, even if we're making progress on a few of these numbers, there's still a long way to go. Therefore, scientists of days don't spend much time debating Drake's list, even if it can be a nice conversation starter and a valuable way to frame the difficult problems surrounding the possibility of extraterrestrial life. They instead measure things more narrowly, using the habitable zone. In any case, a planet may not be necessary for life to flourish in the cosmos, but it does offer an exceptional setting in which the advent of life is met with a multitude of favorable circumstances. This indicates that some degree of chemical enrichment, a high enough percentage of elements heavier than hydrogen or helium, had to have developed before the star and stellar system formed. When the number of known exoplanets surpassed 5,000 in 2022, a stunning collection of information was gleaned by examining whether stars had any planets at all around them. Nearly every planet, 98.2%, was discovered around stars that had at least 25% of the heavy elements present in the Sun. There were no planets at all identified around stars with less than 5% of the heavy elements present in the Sun, and the remaining 1.8% of planets were located around stars with between 5% and 25% of the heavy elements found in the Sun. We need enough heavy metals in the environment if we are to have a rocky planet that supports life as we know it. This constrains the locations where such planets may develop in the evolved galaxies of the current universe. Planets supply the building blocks necessary for biochemical processes that enable life, but energy sources are also necessary for life to form. We know that the Sun provides the energy that powers nearly all forms of life on Earth, even though other plausible sources such as volcanic activity, tidal forces induced by a parent planet or large moon, radioactive decay, and other internal and external sources could also provide such a source. But the kinds of life-friendly planets that might emerge are severely limited when a world's life is powered by a star. To start with, you need to be in a favorable position in relation to your star. The extreme heat, winds, and radiation from your parent star might cause things like atmospheric erosion or surface heating to the point that only lava-based liquids can exist on Earth's surface if you happen to find yourself too close to it. Similar to this, if you are too far away from your parent star, you will get too little energy from it and become too frigid for life to survive on the surface. This is the concept underlying what astrobiologists and astronomers refer to as the habitable zone, which indicates the point on a planet's surface where liquid water will be conceivable given an atmosphere similar to Earth. The temperature, brightness, and total energy output of each star determine its own habitable zone. The habitable zone will extend farther and broader from the star the brighter your star is intrinsically. The habitable zone of your star will be closer to it and narrower the colder and fainter it is intrinsically. The habitable zone in our own solar system is believed to stretch outward to roughly the location of Mars and maybe a little bit beyond, but inward from Earth's orbit to a distance that is just somewhat more than Venus's from the Sun. Many scientists think that, even over extended periods of time, Mars may have been just as conducive to life as Earth is, provided it had been a little bit bigger and more enormous. For stars that are heavier than the Sun, though, this presents a significant challenge. You see, life cannot exist on a planet until it has had time to cool down when it first forms. At least according to our current knowledge of life, a world blanketed with volcanic activity and with the only seas burned away into the sky is not exactly what one would call life-friendly. For stars, the mass of the star, which is closely related to its inherent brightness, also affects the star's overall stellar lifespan. This suggests that stars with masses more than around 1,500% of the Sun's mass could not be suitable places for life to form and persist. As they say, the flame that burns twice as bright lives just half as long, but the reality for stars is even worse. It should come as no surprise that stars with higher masses shine brighter than those with lower masses, since stars with larger masses have more fuel in their cores to generate nuclear fusion. Perhaps more unexpectedly, though, is that a star's maximum temperature and core volume where nuclear fusion may occur at temperatures higher than 4 million K increase with star mass. Additionally, a star's core burns up nuclear fuel more quickly. Upon summing up all the cumulative impacts, the lifespan of a star twice as big as another is reduced to 1/8, or 12%, of its original mass. Furthermore, planets only have a limited amount of time to maintain life before their parent stars heat up to such a degree that their seas boil away and all biological activity is sterilized. This is because stars evolve by heating up throughout the course of their lifetimes. If life had started on a planet around a much more massive star, it would have been sterilized long before it could have developed into something sophisticated, differentiated, and intelligent. On Earth, we probably have another 1 billion or 2 years before that happens. Simply said, planets orbiting more massive stars run out of time. However, this may make stars less massive than our Sun even more desirable long-term hosts for life. This may initially seem illogical because planets around the stars with the longest lifetimes, the low-mass stars that astronomers classify as red dwarf stars or M-class stars, face two main issues that aren't present on a planet like Earth, which orbits around G-class stars that resemble the Sun. For hundreds of billions or even trillions of years, stars with masses less than the Sun may survive. The lowest mass stars can last for as long as 100 trillion years. Although serious, these two issues may not be life-ending obstacles for them. Tidal locking is the first one. The timescale during which the less massive body gets tidally locked to the more massive one depends on the distance between the more massive parent body, such as a star, and the less massive orbiting body, such as a planet. The reason the Moon always faces one direction when it is in Earth's orbit is due to a phenomenon known as tidal locking. In only a few million years, all planets around M-class stars will experience a phenomenon known as locking, in which they will have one extremely hot side that faces their star constantly and one extremely cold side that never gets direct light from their parent star. Since the planet only rotates on its axis once every orbital revolution, many planetary scientists believe that the planet's severe and permanent temperature disparity is caused by this tidal locking, which is detrimental to life. However, the planet's tidal forces will heat the planetary core, which may allow for the creation of an unnecessary protective magnetic field and increase volcanic outgassing, both of which may help to save the atmosphere from being destroyed. Liquid water and maybe life might be made possible by atmospheric circulation in areas that stretch widely onto both the day and night sides, rather than only in a small ring at the boundary between day and night. Put another way, even though this tidal locking may appear strange to us on Earth, it may not prevent life from emerging and flourishing. However, planets orbiting lower mass stars also have to deal with a second significant issue. This is a significant issue that is connected to flaring activity. All of the low-mass stars we have observed remain incredibly active and variable even billions of years after their birth, in contrast to a star like our Sun, which is only incredibly slightly variable, changing by no more than 0% over even the extremes of the solar cycle and increasing by only a few percent every billion years. Large, sun-like star patches that may engulf up to half of a red dwarf star's surface are present. Even though they generate far less light than the Sun, they regularly produce powerful flares that are rich in X-rays and ultraviolet radiation, which can completely remove the atmosphere of an orbiting planet. There's a major disclaimer to the widespread speculation that this kind of star activity makes these planets totally inhospitable. For the moment, however, remember that our Sun and every other star were once similarly active, producing a great deal of flares and regularly releasing particles and radiation that ionized the atmosphere. However, a star like our Sun eventually enters a more stable phase that allows a constant radiation dose that scarcely changes in temperature or strength to affect any planets in its orbit. We recognize and consider this stable period to be a collection of circumstances conducive to life. It turns out that a star's mass affects how long it takes for it to settle down. It might take hundreds of millions or perhaps billions of years for K-class stars, the class that lies between G-class stars like our Sun and M-class red dwarf stars, to enter a stable phase. However, older K-class stars have been seen to attain this continuous emission condition. We fully expect that red dwarf stars will also eventually enter a stable phase, although on timescales longer than the universe's current 13.8 billion years. Volcanic activity has the ability to restore the atmosphere of an orbiting planet, even if it is stripped away early on. This suggests that life may develop on such a world far into the future, many billions of years from now. But stars will stop forming at some point, a very long period from now. Since its peak 11 billion years ago, the rate of star creation in the cosmos has been declining. It currently stands at around 3% of its maximum and is still declining. A galaxy no longer has material that can be used to generate stars when it has completely lost its gas. And thus the stars with the largest mass and the shortest lifetime start to fade away over time. Massive galaxies near the centers of large galaxy clusters become red and dead the fastest, while isolated gas-rich galaxies will last the longest, engaging in what is known as quiescent star formation for up to trillions of years to come, or possibly longer. After a few billion years have passed, only the lower mass, redder-colored stars remain, and these galaxies become known as red and dead. In regions where star formation occurs more slowly, almost like a trickling as opposed to in large bursts, such gas-rich galaxies may continue to generate stars for up to quadrillions of years. Brown dwarfs, or failed stars, will ultimately spiral in and join, making up the last group of things that light up the universe before it all ends, even after that ceases entirely. Once they reach that point, if their mass is high enough, they can initiate fusion to produce a red dwarf. Once that star enters a stable phase of its existence, life may originate and flourish if the planetary circumstances on any worlds around it are exactly perfect. Together, these clues lead to the following possibilities for life. Of the stars in our galaxy, the lowest mass ones will only become habitable after hundreds or even trillions of years have passed, and they may stay habitable for as long as \10^14 or 100 trillion years. Up to \10^17 or 100 quadrillion years in the future, new star formation may provide fresh opportunities for life to those stars that haven't formed yet. The stars that result from the eventual mergers of brown dwarfs might not stop burning for \10^21 or 1 sextillion years, at least, until gravitational interactions completely eliminate what we refer to as galaxies from the universe. There is a lot of mystery and ambiguity around all of this. After all, Earth is still the only planet that we are aware of where life has ever developed and is still thriving, even in 2024. Even far into the cosmic future of our universe, there are still a wide range of probable scenarios for life, at least life as we know it. In a universe full of planets and biological possibilities, past, present, and future, our cosmic home may not be livable for a very long time. But it would be naive to think that the course of events as they have played out here is the only logical route to success. Some of the worlds we've found in the search for extraterrestrial life are thought by experts to harbor alien life, which humans may eventually settle on. Here's a quick rundown of a handful of them. 1. Kepler-186f. Kepler-186f is among the most plausible contenders for life as we know it. In fact, we may find it rather easy to inhabit this planet if we could find a way there. Unfortunately, even with extremely generous and liberal calculations, it would take us hundreds of thousands of years to reach the globe, which is 490 light-years away. Found in April of 2014, it is a terrestrial planet within the habitable zone of its star that is just 10% bigger than Earth, placing it firmly in the category of possibly Earth-like planets. In the end, Kepler-186f is only the outermost planet in the Kepler-186 system out of the 5 known planets. Given that Kepler-186 is a red dwarf star, it is much smaller and fainter than the Sun. Even a great comparison between the appearance of a Caribbean sunset on Earth and what a similar location would look like at nightfall on Kepler-186f was produced by the Planetary Habitability Laboratory. 2. Kepler-283c was found as part of a massive data dump from the Kepler Satellite Telescope, along with a plethora of additional planets. A startling 700 fresh verified exoplanets were found in this data. Remember that there were none known 20 years ago, so 700 planets in one solar system is rather amazing. But the ability of this planet to host life akin to Earth's is just about gone. It orbits substantially closer to its host star, which is more than 1,700 light-years away from Earth and is roughly twice the size of Earth. However, the star is still firmly inside Kepler-283's habitable zone despite its diminished size. 3. GJ667cF and GJ667cE. These planets, which are members of a triple star system, have 3 suns each, making for an incredible sight. These are 2 of the most bizarre worlds we have ever seen that may be livable. Both planets, like the other worlds discussed, are inside the habitable zone of their star. Although they are just 22.1 light-years distant, getting there would still take some time. It would be somewhat more doable. 4. Kepler-62e and Kepler-62f. These planets are Kepler-62s, which are additional worlds found by NASA's Kepler Space Observatory. As their names imply, given that Kepler-62e is around 1.6 times more massive than Earth and Kepler-62f is only roughly 1.4 times more massive, these planets provide a little bit more leeway for maneuvering. These worlds move between 1 and 200 light-years from Earth in the constellation Lyra, which makes them rather far away, at least from Earth in terms of human travel. You would be significantly older now if you were born on Kepler-62e. Every 122 days, it completes a full orbit around its red dwarf parent star. The orbit of Kepler-62f is around 267 Earth days long. It's believed by researchers that both 62e and 62f are water worlds, which are warm locations that are partially or entirely submerged in liquid water. As such, seeing them would undoubtedly be incredible. Just think of how enormous the whales may be. Long-term residence there, nevertheless, can be a little challenging. 5. Another one of our galaxy's neighbors is GJ581d. At only 20 light-years distant, it is essentially right around the corner in the big scheme of things. The planet listed here that is nearest. The planet may, however, have a dense carbon dioxide atmosphere, which would make it fairly uninhabitable given that humans require oxygen to breathe, even if it is close by and in the habitable zone of its star. It might not be too magnificent for us, but experts think it could have breathtaking rainforests since they think it might be rocky with liquid water. But even if it did have oxygen, it would be somewhat harder for people to survive there given that it is around twice as big and 7 times more massive than Earth. Nevertheless, if we ever develop the technology to use interplanetary travel, we might want to give it a shot given it is practically in Earth's backyard. Finally, keep in mind that the James Webb Space Telescope is studying the TRAPPIST-1 system, which has 7 Earth-sized planets, 3 of which are in the habitable zone of its luminary. We certainly live in an exciting time when we can gather light from a small rocky world in the habitable zone of another star and examine it for evidence of life for the first time ever. It will take time to gather enough light and process the data. Stated differently, the long-standing topic of whether or not there are other extraterrestrial Earths exists is about to have its answer revealed. Take in the breathtaking sky, identify your favorite star, and give yourself permission to ponder the possibility that we are not the only beings in the universe. That's all the information we have for you today. Share your opinions in the comments below. Thanks for watching another episode. While you're here, you can watch more space-related video.